In the first class itself, we discussed about two types of analytics problem, right? One is classification and another is regression type problem, right? If you remember correctly, I don't know if you remember, but if you remember, I spoke about two types of problems. Okay? One is classification. Okay? Just be casual and just try to understand in a layman. Okay? Don't take it from academic. Then this is regression problem, where I just want to know if my x variable increases, how my y variable is increasing. Whereas this is classification. There are circles, there are cross marks. I want to classify them somehow, right? Right. So there are two types problem. This is called classification problem. This one is called regression, right? Now we have already learned about regression, right? So we just need to know in both the cases we just need a regression line, okay? But yeah, primarily there will be some fundamental differences will be there, but more or less the same, okay? So now we know what is the regression line. Y is equal to beta naught plus beta 1 x, right? This is known as independent variable, right? This is known as dependent variable. Beta naught is slope coefficient, beta 1 is beta naught is intercept, and beta 1 is slope coefficient, right? So this is a quick recap. Now we have learned single variable linear regression, or we call it as simple linear regression, where we have only one independent variable, right? Y1 is equal to beta naught plus beta 1 x1. But we may have x1, x2, x3, right? Many more variables. So when we have a regression equation like this, x1 plus beta 2, x2, and so on, we call this as multiple regression, multiple linear regression. Okay, clear? Now, why? The question is why we have this separation? Why we have the distinction? Okay, why do we distinguish between one variable regression and multiple variable regression? And be careful. Okay, just be attentive. So another reason why is because we want the independent variables to be uncorrelated. Okay, so the correlation between independent variables should be as minimum as possible. Okay, so that's why we just classify, and we also have some more problems. What is known as the error term should not be correlated. Okay. The problem that arises when you have correlation between your independent variable is known as multicollinearity problem. Okay, and the problem that arises when you have like correlated errors is known as problem of autocorrelation. Okay, now what is that fixture? I'll cover later on, but now till this point is clear.
That error term should not be correlated with some.
Yes. So what is error term? Understand what is error term? Right? Error terms means, for example, you have error 1 in the first observation, error 2 in the second observation, error 3 in the third observation, right? And then you have error 4, error 5, error 6, right? These errors should not be correlated. So this is one series, this is second series. There should not be any correlation between these errors.
If error 1 increases, error 2 also increases.
There should not be correlation. And there is an assumption actually. So don't try to get into the deep, it will be very confusing. I'll tell you why it is important.
Maybe doing that beta naught,
right?
Beta naught plus beta 1 x, beta 2 x, beta 3 x, something like that. So does that mean that we are considering different lines?
No. That's not possible actually. We cannot have a regression line on plane when you have more than one.
So on the same line you're drawing different points?
No. It's not possible. You cannot draw a line actually, because beyond 3-point dimension we cannot have a fourth dimension. Right?
So what does that represent actually?
You cannot represent it individually. You cannot visualize it. It's just some data points. Just imagine that there is a n-dimensional plane where you have n variables and all that. It's just imagination. And I think it's pretty much there in almost everything, whether it's physics, whether it's mathematics, everywhere. If before beyond 3 dimensions, we cannot visualize. You have x, y, z maximum. It's like you see this house, right? You have length, you have breadth, you have height, but you cannot have 4th dimension after this, right? You got the point, right? So, yeah. Now let us first learn what is multicollinearity. Okay, so now this is a very interview question actually. Then people ask. Okay, the problem of multicollinearity one happen when your x1, x2, and x3 they are somewhat correlated. Okay, and why is it an issue? See, you have this equation, right? X3. Okay, say for the 3 independent variables, right? Now, when we interpret this coefficient, right, we assume one thing that when we keep these values constant, if I increase x1 by some points, what is going to be my impact on y, right? But keeping all these things constant. For example, if you are comparing my salary with your salary, right? But we need to keep constant what? Our experience level, our education level, right? People with different experience level, different education level, if you compare the salary, no point. Right? So you have to keep everything constant and then increase one variable, right? Now what happens is that when two independent variables are correlated, say for example x1 and x2 are correlated, if you increase x1, x2 will automatically increase, right? Because they are correlated. Now that assumption is violated, that keeping everything constant it will increase. Now we cannot keep everything constant because these variables are correlated, right? So ensure that when you have variables, you should not use correlated variables. Now I'll give an example. Your gross salary or net salary. One of the variable is that, say for example, x1 is your gross salary, x2 is your net salary. Do you think these two variables will be correlated?
Yes.
They will be very correlated. They will be like 0.8, 0.9 correlation, right? You'll find 0.9 correlation, right? That means you cannot say that, okay, given my gross salary constant, what is the increase in net salary? That's never going to happen, right? It will automatically increase, right? So in such scenarios, we face an issue called multicollinearity. Okay, just watch this video on multicollinearity, how we detect and how we get rid of this. Okay. Important thing. The next thing is autocorrelation. Now, as I said, autocorrelation problem happens when we have a measurement for different time period. For example, we have this variable x1, which is marks scored by same set of students for different years. Okay. For example, particular student has scored 50 marks first semester or first year, 60 marks in the next semester or next year, 70 marks, right? So same agent or same student and his marks in different time periods. So there will be correlation, right? My marks this semester is correlated to my marks in next semester. Is it right or not? Because I am the same person. Now today I am an average student, tomorrow I will not be a genius. Right? I will again be average student. Probably there will be a slightly increase in the marks, but still there is a correlation, right? That's why when you have time series data means data points collected at different time period. Okay, you collect data, say sales data for 2005, for 2006, 2007, then this data will be correlated. In these cases, we face this into the problem of autocorrelation. Okay. Now, I also have a video on problem of autocorrelation. Okay, just watch that video. What is autocorrelation problem and how we get rid of this problem. Clear, right? Okay. So we learned about what is multiple correlation, right? Now we will learn what is classification. Now, I'll start with an example. Okay. Now here is the student. Okay. Then I have his GRE. You know what is GRE, right? GRE score, right? If the student GRE is 780, okay, his gets admission. 800 gets admission. 600 no admission. 790 no admission. 680 admission. 0720 no admission. 7. Okay. Now I have student and the corresponding GRE score, and whether a student is admitted or not in a college, right? So I just need to know, looking at somebody's GRE score, can I say that whether he is going to, what is the probability that he is going to get admission, right? Probability. So probability value lies between 0 to 1, right? Yes or not? Right? So I just need to know what is the probability that a student is going to be admitted, right? So when you put it in a plane, so if these are, you have this GRE, right? Okay, this is like, not getting admission, and this will be like getting admission, right? So you will try to fit a regression line which will pass through this middle. Okay, there will be some misclassification, right? But this line says that after GRE score, say x1 GRE score, you get all admitted, and before that you got all non-admits. Right? So this is a classification. How we do that? You use a special type of regression known as logistic regression. Correct. Now let us learn what is logistic regression. Logistic regression takes a form like this. Okay, or x1 is the independent variable. Okay, y is independent variable, but y is represented in this form, logarithm of p by 1 minus 1. Okay, p is nothing but probability of event. So event here is getting admission, right? 1. What is the probability that, or probability that y is equal to 1? Stop me when you are in doubt. Okay, please. So probability that y is equal to 1. Here, what is p? Probability that y takes 1, or the event has happened. So event could be getting admission, death of a person, customer who leaves the company. So you can take any event. So logistic regression is primarily used to get the probability that a particular customer is going to buy your product, or some event is going to happen. What is the probability of that? Right? The less the probability, less chances are there. More the probability, more chances are there. Yeah?
What is this? Y is equal to 1. So you're keeping it. Sorry, I mean, I couldn't understand this.
No, the probability that y equal to 1. Probability that y equal to 1. So this will be like between
1 in the sense that he's getting admission.
Yeah.
0 and
yeah. I'm sorry, I didn't mention. So when it takes 1, it get admission. Okay. So when it takes 0, we call it as non-admit. Okay, no admission. Clear? Right? So this is event and non-event.
Here, some point is that probability is less, then less chances to more or something. And on what basis we can define that probability is more or less.
Yeah, I will come to that. Okay. Okay. So what happens is that once you have this regression in line, this regression form, when we estimate it, finally we come up with probabilities value. Okay. Now against each, let me go back. Against each student, right? This is historical data. When you do the regression, you will have the corresponding probabilities values. Okay. Say for example, 0.6, 0.4, 0.5, 0.6, 0.7, 0.3, 0.4. Okay. Now we can set a cutoff value, something like that. Okay, say 0.5 is the cutoff value. So people with probability score greater than 0.5 I'm going to get admission. Who are going to get less than that? I'm not going to get it. Again, if there is no rule of thumb that 0.5 will be there. In industry, generally it depends on so. Okay? Usually we take 0.5 as the touchstone.
This probability score will be given there.
Yeah, that's the main output from this equation.
Okay. Division will find out the probability.
Probability, like when we are taking a 0.5, does that mean there's a significant 5 and 50% chances of occurrence? Something like that?
Yes, it's significant chances. That's right there. So now we learned what we learned. We learned two important concepts of multiplication. Now let's show why we do multiplication separately. Why we have a separation between linear and multiplication. Right?
One question I wanted to still ask. If you go back.
Okay. No problem.
Might be repetitive. But then what I wanted to ask is like we are taking these values, right? So this x1 and b1, I mean these are slopes, right? b1, b2, b3. So are we taking this on different lines? Are we drawing different lines?
No, it's not possible actually. See,
what I am
asking is suppose
not in real sense.
This is the reaction. You are saying are you having different lines?
Yeah, that is.
I mean same y and different x1. We have only one x1, right? How can you have x2 here? See, y, this axis, right, can take only one value, right? How can you have, say, for example, x1 is your age and next is your salary? How can you have age and salary onto one line? That's mathematically impossible, right?
I mean, we do not have y here, right? We are calculating y based on x, right? So age is somewhere here. I mean, say age if you take.
How can you take that's y, right? You calculate y variable always. When you plot it, you always have y.
So what does this mean exactly? I really couldn't understand still.
Which one?
I mean, in case of linear, we are very clear that we have a single line,
right?
And we are taking instances on the same line. Right. What does this signify? I mean, what is the
extra variables?
Yeah. What does this signify? I mean, what
again? It's a line only. Unfortunately, we cannot plot it. But still,
okay,
it is a line.
Okay, it is a line.
Still. Can we take that example of mileage car? We can compare with this x1.
See, I'll tell you. Let me show you 3-dimensional.
One more question. Does this happen in real scenario?
Yes, obviously this happens. This is pretty real scenario, right? Your house price, I took the example house price, right? House price doesn't depend only on your square feet, right? It depends on many variables. So based on many variables, you find out your volume.
So that are these variables, different variables.
Yes.
But then we are signifying x as certain. We are relating
yes,
x to
these
certain
are x variable only. These are x variable. All these variables are x variable. Now your question is what you show me it on plot. Unfortunately, God has given us only 3 dimensions.
I am not saying that. What I'm saying is like say in case we are considering weight of car as one of the variables, and we are considering weight as x, and then we are looking at the size of car as another variable, which is x2,
right?
So we cannot plot it on the same thing, right? So then why and how exactly are we deriving these things?
Deriving is very simple. You just add it up. So why you want to plot it? Why? Just see, this plotting is just a child game, right? When you teach somebody, right, a child, then you actually plot it just like you're going to visualize, right? Now the moment it gets bigger, you cannot do that. You are helpless. Unfortunately, you cannot plot it. But your point is see that doesn't make sense. Too many variables and then one y variable. How do you visualize it? Unfortunately, we cannot do that.
And like in real scenario, then I agree. Like we cannot do that. But then in real scenario, how do we calculate b2, b3? Because we do not have some plot, right?
But oh my God. It's like it's the end of Ramayana and you are saying how can we do that? Why you cannot use a dy by dx1? This is derivative, right? Okay. You can calculate dy by dx2. You can calculate dy by dx3. What's the big deal? Mathematically it's possible. You do not plot a line and then find its slope and not. It's done mathematically. It's not like you go and stretch a line and then you calculate its. The software doesn't do that.
Just trying to understand.
No, that's fine. That's a very good question. I am not saying this. In fact, it was a question in mind also for a long time. But how do we visualize it? We cannot do visualize. Okay? But you always remember one that any variable you will take, whether it's house price, whether it's a car, mileage of a car, it always depends on more than one, right? And we can take a mathematical form where this variable is a combination of so many variables, right? With some estimates. That's the most interesting part. Clear? Let's move on. So I'm stopping here.